seminar today, Dr. Quốc Huy from the Vietnam Institute for Advanced Study in Mathematics, and he will give a talk on reforming cyclic cover in towers.
Okay, thank you very much for the opportunity to talk about my research. Okay, all right, so maybe let me first give the outline of my talk today. So the first part, I will give some motivation. In particular, I will talk about A-tau fundamental groups, actually of object in characteristic P. Yeah, so our main theme is about things in characteristic P and how they relate to characteristic 0. And then on the second part, I will introduce something quite classical, is the Artin-Schreier bit theory, which classify all the Z mod P to the N covers of curves actually in characteristic P, hence on cyclic covers. Because, you know, for some reason, understand like these cover in characteristic P is enough for all cyclic coverings. And the main result that I want to present is the following: is a deformation of a subcover of curves on way extend to the whole tower. Right? You have a tower of covering and you have a deformation of the subcover, then you can on way extend that to the whole tower. And in order to do so, I will have to introduce Cato's refined Swan conductor, a very powerful invariant that help us to understand the good reduction of a cover. Okay. All right, so let me first go to the motivation, fundamental group in characteristic P and characteristic 0. Okay, so if we start with C is any curve over K, where characteristic of K is equal to P. So when I say curve, I mean smooth connected curve. Then Rothendig showed that C always leads to a curve C stripped over the bit vector over K. Right. So that is the bit vector, the drawing of bit vector over K. So one example of bit vector is when, for instance, if K is say FP, right, very simple one, it's perfect, then WK is just the ring of periodic integer, a very familiar object in number theory, and in characteristic 0. Right, so it always leads to characteristic 0. Any curve leads to characteristic 0. And if we let C strip eta to be C strip generic fiber, then also by Rothendig, the prime to P part. Yeah, so this notation means the prime to P part of the A-tau fundamental group of C is equal to that of the generic fiber. Right. So just recall this one is in characteristic P and this one is in characteristic 0. Right. So that's how you relate characteristic P to characteristic 0 through the lifting process. Quite nice. But first, what is meant by prime to P? So if you start with any finite group, right? G is any group, then you can have the group that generated by on the 0P subgroup. So that is going to be a normal subgroup, right? So the prime to P part of G is nothing but the quotient of G by H. And because the A-tau fundamental group is profinite, is a profinite condition, you can extend the definition of prime to P part, right, to a profinite group. Okay. Any question so far? Okay. And the upshot is the right-hand side can be computed quite easily, right? The right-hand side in this equation can be easily computed using topology. Namely, the A-tau fundamental group on the right-hand side is equal to the complex point, right? Because you take, the algebraic closure, you may change to the algebraic closure. So it should contain the complex point, the complex field, and then you just take the complex point. So you obtain a complex variety, thing like that. And this one in turn is equal to the profinite completion of the topological fundamental group. And the profinite completion, the topological fundamental group of a curve, right, is of a Riemann surface is known. It's just classical in topology. So the prime to p part of anything in characteristic P is quite easy to compute. However, the P part is different. For instance, the A-tau fundamental group of the affine in characteristic P is non-trivial. Even the 1 over complex in characteristic 0 is trivial, right, because it is contractible. The reason is there exists a non-trivial A-tau Z-mod P cover that's given by the equation over here. Right, so this one is called an Artin-Schreier equation. Right, so if I think I should say that we identify, A1C with the spectrum of A1K. Right? We identify A1K with spectrum of KX. Yeah, so the equation here would give you a Z mod P cover, hence it contributes to the A-tau fundamental group, and it is non-trivial. In fact, until now, we still don't know what is the A-tau fundamental group of the affine line over K. It's still a mystery, because understand them, we have to understand a lot about number theory. But we know a little bit. We don't know the whole group, but we know the quotient of the group. Right? So what we know, maybe I should say a little bit, is if Chi is a quotient, right? So if Chi corresponds to a Galois cover, Chi is a quotient of the A-tau fundamental group. Then firstly, from the above equation, we have that, don't want the arrow like this. From the above, we have that, we can have that the prime to P part should be trivial, right? Because, we have this one is trivial. We have the 1 over complex is trivial. So the prime to P part of any portion of the A-tau fundamental group is trivial. And also, we also have the inverse. So the inverse direction, let's say any group that the prime to P part is trivial, or any P group, actually, any P group is a Galois group of a cover of the affine line over K. And the inverse direction is proved by Renault in the 90s. So this one is usually known as the Appian-Carr conjecture. So that's what we know. We know the quotient, but we don't know how they fit together. So we don't know the profinite completion. That's the issue. Okay. All right. So maybe let me talk a little bit about A-tau fundamental group of an elliptic curve. For those who are familiar with number theory. Right. So we see that the A-tau fundamental group of the affine line over K is larger than 1 over complex. But it's not always the case for any curve. For instance, if you consider E over K is an elliptic curve in characteristic P, right, we may assume K to be algebraically closed. Now, to make it simple, then in fact, so first maybe talk about characteristic 0, right? So we know the E here always lead to E tilde over the bit vector over K, for example. And we know that maybe over complex to be simple, then an elliptic curve is just a torus, right? A complex torus. So an elliptic curve gonna look like this. And so because there are two kind of circle, one like this and one like this, two kind of loops. So it means that the A-tau fundamental group, the A-tau fundamental group of E tilde, maybe I should say the bar, when you take the algebraic closed field, taking the base chain, is isomorphic to Z, the profinite condition square, right? Because we have two generator in the free group of two generator. Yeah, and this one is of course is isomorphic to the product of all the prime ZQ square. Yeah. Okay. Any question? Yeah. So that's what it looked like over characteristic 0. But characteristic P is actually smaller. So in characteristic P, actually the one in characteristic P is you either have, well, I just copy the whole thing here. Yeah, there are two cases actually, Q prime and Q different from P, right? Everything is Q prime, Q different from P when E is it's called super singular, whatever it is. So, and yeah, so it actually smaller than the 1 over complex, and the same thing, and you also have the other possibility is that times Z mod P when E is ordinary, so it's an ordinary elliptic curve. Yeah, so super singular simply mean when the P torsion is trivial, and ordinary mean the P torsion is what it is. It's symbol, yeah. It's like this. Okay. Yeah, so it is actually smaller, right? As you can see. So yeah, so should be careful about that. Not anything characteristic P have bigger fundamental group. Okay. Questions so far? All right. Yeah, so right. So that's what I want to say. So now let's go to right, because of the reason that we want to understand the A-tau fundamental group of the affine. Oops, I think go over K. Right. So we want to understand their covering. For in particular, the covering when the Galois group is divisible by P. The order of the Galois group is divisible by P. Right. So, and one of the most simple among them are cyclic covers, right? Because cyclic is the most simple group. Right. So we want to start with this. Right. So from now on, we will study cyclic coverings of curves in characteristic P. Then what we have is the following. So that what I will present is something called the Artin-Schreier bit theory. That help you identify cyclic cover in characteristic P. So if I start with phi n to be Z mod P to the n cover of the projective line P1K, then any such cover is given by this equation. So this equation is called an Artin-Schreier bit equation, where all the operation are bit vector operation. Right, on the sum, the product bit vector operation, and all the entry are also bit vector, of course, where the left hand side is variable and the right hand side is simply a bit vector of length n. Yeah, I call it this one is a bit vector of length n. Right, so when you have infinite bit vector, then it's in characteristic 0. But now you have finite length bit vector is still in characteristic P. Bit vector of length n. Right. So that is nice, right? And even just a little bit technical, then the right hand side is unique up to adding something like this, where this one is just the Weierstrass P, it's just the propinous subtract to identity. Whatever it is, it's not too important. Stop. Right. So where these things come from? So actually, this one is right. The one thing, one perspective we should consider is from group cohomology, because the phi n that we consider can be think of as a character, right? An element of the group H1. This one stands for the absolute Galois group of Kx. The absolute Galois group of Kx. With coefficient in z mod p to the n, and this one is a group homology, right? Because you can, think of this guy as vpn, vp to the n, right? The group of p to the n root of unity with coefficient in Kx, right? So number one, the above is actually follow from a result of Hilbert 90. That's one is actually from Hilbert theorem 90. Let's say the left-hand side is isomorphic to a bit vector of length n mod out by the Weierstrass operation. Okay. Right. So when we think about something as a character, then we can apply representation theory, and we can talk about their product, right? We can talk about product of character. So it's nicer when you think about it this way. Right. For instance, when you're taking the power of the original one to the p to the n minus I, then you obtain the z mod p to the I subcovering. And it's given by the first I entry of the original bit vector of this one. Just, you have from this one, you obtain this one. Okay. Just a quick review, because I will not use this a lot, but to get some taste about the technique that we're going to use. Let's look at some example. Right. So when p is 2, then the equation over here, because it have 2 entries, right? So it's a bit vector of length 2. So actually the equation here gonna give you a z mod 4 cover of a projected line P1K. And moreover, so if you look at the bit vector, can tell you about the ramification of the covering. For instance, in this example, if you count the poles, you see it had pole at 0, it had poles at 1, and it had poles at A, right? Maybe I say A different from A different from 0 and 1. Okay. Then if you look at the ramification diagram on the corner here, right, this corner, the ramification diagram, then the information about the poles tell you that the cover branch at 0, at 1, at 0, at 1, and at A. Right. Moreover, because 0 and 1 appear on the first entry and A only appear on the second entry, then you see the difference, right? So it tells you that, well, the inertia group at this point is z mod 4, and the inertia or the stabilizer of the z mod 4 action at a point above A, a ramified point above A, is z mod 2. And even more than that, it tells you a lot about the ramification of the covering, but just want to give a few. Right. Okay. Question. All right. So now let's talk about deformation. That's the main goal of this talk. Right. So if you start with a Galois cover of curve, fine. Suppose A is a complete discrete valuation ring with residue field K. So A here, some example is A can be the power series over K. So this one is in characteristic P, and A can be bit vector over K. This one is in characteristic 0. The residue field. Then a deformation of phi over A is nothing but, well, something like on the dry vertical arrows. Right, some cover tau of X over A, of X stripped over A, where, of course, you want the special fiber is isomorphic to the original one. See, we want the, so this guy is, the special fiber is isomorphic. The special fiber of tau is isomorphic to phi. And also, the original one had a chi action, right? It's a chi Gawa cover. So you should have the chi action on Y stripped that reduced to the original one on Y. Yeah, so the action in here reduced to here. So all the information should be compatible, should be nice. Then we call tau with the root action is a deformation of phi. And the deformation functor we usually denote by def phi of A. Def phi, yeah. Oops.
May I have a question?
Yes.
So the action of G on curly Y, is it automatic or is it the assumption?
The chi action, yeah, so it's a chi Gawa cover. Is that what you're asking? The
So you have the channel action on the left, and
yeah, so
you say that the requirement
the group of Y that fix X is isomorphic to G. So you have a chi action in
so
here.
this is the assumption of the deformation. It is in the definition.
Sorry, I cannot hear you very well. Can you repeat?
Oh, so the question is the action, the G action on the right hand side is the assumption of the deformation, right?
Yeah.
Never mind.
Yeah, so it reduces. Yeah, so you start with a chi action on the left, right? And the deformation. So when you have a deformation, then you have a cover with the root action. So it's just a chi Gawa cover. Yeah, it's just a chi Gawa cover on the right, so that the chi action in here, when you restrict to the special fiber,
okay,
isomorphic to yeah. I think that is the good way to think about this. Okay, like, does it answer your question?
Okay.
Any other question? Okay. Right. So, and one of the upshot of deformation is, when you have a deformation, when you understand the deformation, you understand a flat family, the flat family containing phi, right? Any flat family containing phi, and yeah, one of the most famous application of deformation, not deformation of chi covering, but in different context is for the Fermat-Last theorem, right? Yeah. So in the Fermat-Last theorem, one of the main tasks is to identify elliptic curve with what modular form, right? Modular form. Yeah. So instead, with elliptic curve is quite complicated. We want to relate to representation of elliptic curve, because elliptic curve is a root, so you can talk about representation of a root. Representation of elliptic curve. All right. So what Wise do? What he did is show that, well, if rho is a Galois representation of an elliptic curve, so if rho in here is modular, whatever it is. All right. So if a representation is modular, then so is everything in its deformation. All right. Then so is everything in the deformation of rho. And he even calculate these things, right? So we know all the deformation of rho, and that helps us to extend the correspondence between elliptic curve and modular form. And that is one of the key things in the proof of the Fermat-Last theorem. That is just what I know, but it's much more than that. Okay. Yeah. Okay. Yeah, but we will not talk about representation of elliptic curve, the deformation of representation of elliptic curve. Yeah, we will talk about deformation of chi covering in this one. Okay. So let's maybe look at one example. Right. So again, if you start with phi is a Z-mod phi cover, I should say the characteristic is phi, then the equation over here give you a Z-mod phi cover of a projective line in characteristic K. Right. It is Artin-Schreier theory, something I have talked about. And if A is K double bracket T, then the tau that given by this give you a deformation of phi over capital A. So why is that? Why is tau is a deformation of phi? Well, one of the things you can see is, so if you look at the special fiber, right, is when T is 0, right, the special fiber. If you look at that, you will see that you plug in 0, T is 0, you have the right hand side would become 1 over x to the 6. So they coincide with the right hand side of this. Yeah, so it's nice, but it's only tell you that the special fiber is birational equivalent to phi. Right, the two things is birational because we have the same equation that define them. So we have the same extension of function field, but we don't know whether it has good reduction or not. Right, so it's only come down to show whether tau has good reduction. Then it will be enough because we incurve, right? So we have incurve to smooth curve, to birational smooth curve, then they should be isomorphic. Yeah, so I think this part quite technical, but maybe ignore this for now. It to show that tau has good reduction, just like in for elliptic curve. Sorry, I try to relate everything to elliptic curve. Yeah, so elliptic curve will be the main theme for the rest of the talk. Right, we no, I mean good reduction. Sorry, the good reduction. We want to show whether something has good reduction or not. Okay. Any question so far? Right. So again, the theme is good reduction, and also you can also deform something in characteristic P to characteristic 0, and that is one example. But I don't want to focus on that. Maybe if we have time, then we can go back. And finally, for the first part, I will give some application of deformation for Galois couplings. And one of the classical one is to compute the invariant of curves, right? So suppose you are given like a cover, and you want to compute of something that projective line, for instance, and you want to compute the invariant of this one, then if you can deform, you know how this one deform to, and you know how to compute the deformation, the invariant of different things in the same flat family, then in many cases you can go back to say something about the invariant of the original one. That classical application of deformation theory. Yeah, and some invariant of curves that we usually consider is P rank, or the A number, or the Newton polygon of the associated L function of the zeta function, whatever it is. And one other application of understanding deformation is to solve the lifting problem for cyclic covering in characteristic P to characteristic 0. And again, I will not go too much into the detail. And one thing that maybe some of you know is the lifting problem that I just mentioned above here. Lifting problem is related to the question about extending connection on the projective line. So connection here should be viewed as a system of differential equation, or periodic differential equation. Yeah, so that is appear in many works, even quite recently. And finally, another classical one is when you understand deformation of something, you also understand the modularized space where the original object is part of. Right. And yeah, I think I did show one of my results in the 20 is to show that the modularized space of Z mod P covering in characteristic P is connected when the genus is large, when the genus of the original cover is large, covering is large, when the genus is large. Yeah, because understand deformation will tell you about the geometry of the moduli space. Okay, yeah. So it means that our task is to, our goal from now on is to understanding deformation of cyclic covering in characteristic P. Of curves, right? Everything is covering of curves. Right. So over curve is quite complicated because, as you can see, cover of curves can have ramify at many points and have kind of like singularities at many points. So now, yeah, but thanks to something called a log-cone-log-bone principle, which is by many people have worked on that by, I think, Bertan and Mazar in 2000. Maybe that is one good reference. Yeah, the U deformation theory. So by Bertan and Mazar say that, so if you are given a covering of curves, Galois covering of curves, then the deformation of the covering is determined by the deformation at each ramified points. Right. So if you look on the ramification diagram on the right, you have a cover that ramifies at a few points. Now, in order to understand the deformation of phi, it's suffice to understand the deformation around each ramified point. Right. And the upshot is, first you can reduce to understand like these deformation of the low-cone extension. And the second one is, well, because if you look at a point that downstairs, then you look at the condition, maybe I call the point here is X, then the condition of the at the point X is just a power series, right? It's just a power series, some K double bracket B. So it suffices to understand the deformation of the extension of power series. So from now on, we will mostly play with power series. And in many cases, you can even go back, right? You have an extension of power series. You can go back to a one-point cover of the projective line, right? The cover. So you can go back to the global. In some case, it can help you to reduce the calculation a lot. Yeah. So now, finally, I can state the main result that I want to present today. It says that suppose phi n is a Z mod P to the n cover. So it's a cyclic covering, cyclic extension of power series, right? Yeah, we're dealing with power series now. And suppose, yes, phi n minus 1 is the Z mod P to the n minus 1 subcovering, and psi n minus 1 is the deformation of phi n minus 1 over R. Right. Where R here is K double bracket T. So I say R is K double bracket T, but actually you can extend to any complete discrete valuation ring in characteristic P. So the main point is it's about deformation in characteristic P. Right. Then the results say that n, we can always extend psi n minus 1 to a deformation of the whole tower to psi n. Right. Again, the picture is, well, given a tower of extension, and if you have a sub-extension and you have a deformation of the sub-extension, then you can always extend your deformation to 1 for the whole tower. Right, we have 1 for the whole tower. That's what we want. Okay, yeah, so psi n. And the reason we care about characteristic P, because characteristic 0 is much more complicated. So let's start with characteristic P first. And also in characteristic P, we can apply the Artin-Schreier width theory. Actually, I should talk about that. Yeah. So how Artin-Schreier width theory help you in this case? Well, so because the psi n here by the Artin-Schreier width theory, it will correspond, the psi n can be represented by a bit vector of length n. Well, f1 to f minus 1 to fn. And similar, the phi n minus 1 is just, yeah, the one over here is just another first n minus 1 component. Right. And so on. And now if you go to the vertical arrows on the right, then yeah, the psi n minus 1 here, again, you can associate it with it another bit vector of length n minus 1. So yeah, it's all come down to the psi n here will must have the form like this. So gn minus 1 and finally gn. So it's all come down to compute the gn right here. We want to compute this one. We want to compute gn, and gn is just a rational function over kx, over rx. Sorry, over rx. Yeah. I just think this one is just a rational. So now it's going to try to find a rational function over r. Even, yeah, not need to be power series for some reason. Right. So that's the first thing, the first upshot about this setup. And the second one is if you consider the spectrum of the one over here, then it is usually can be think of as a open disk, an open rigid disk. So it's an open rigid disk. Then you can apply non-Archimedean geometry to study that. So you can do analysis on that. Open rigid disk, and you can think it's contained in the some kind of like analytic affine line, analytic projective line over a fraction of r. So we can do analysis, and that is the upshot of this. So before we move on, are there any questions? Right, so now what is the big picture of the whole thing we want here? So the picture is, suppose we are given left hand side. Sorry, is that like noisy from my part? Can you hear me well?
Yes, we can.
Yeah, I can hear you well.
All right, okay. Do you hear like a lot of noise? Because I think there's some people around talking.
No, it's fine.
Okay, all right, that's good. Okay, yeah, worry, it's noisy. Right, so yeah, we are given what we are given is an extension, a tower of extension of power series on the right hand side, and also yeah, we are given a deformation. Right, a deformation can be think of as a cover of a disk on the left hand side of psi n minus 1. Now our task is to extend the deformation here to 1 for the whole tower. Yeah, That is our goal. Yeah, to construct something like this. Right. So yeah, use too many highlights. Right. So I will give maybe an overview of the proof. Right. So what we're gonna do? Well, so what we're gonna do? So it's hard to construct a deformation to the whole disk. But what we do is, well, we first look at some subdisk of this one, right? We have a subdisk, and we look at the restriction of psi n minus 1 to the subdisk. Then, with some good choice of the subdisk, we can extend. It's not too hard to extend like this. Not too hard to do extension when the disk is small enough. Then now our goal is to somehow expand the construction, right? So the disk here gives you some rational function. Now you can modify the function, right? So the subdisk would correspond to some function, say gn tilde, some rational function. You give it. So now the key is we can modify the gn tilde a little bit in order to expand the construction. Now we want to keep expanding and expanding and expanding until we get to the whole thing. Yeah, we keep expanding until we get to a cover of the whole disk. Right. Yeah. So now one question occur, right? One question occur, like how we know whether our expanding is good. How we know we're expanding is good. Right. So it go back a little bit to the deformation of the subcovering. Then in fact the phi n minus 1, the information of the phi n minus 1 is actually encoded on the boundary of the disk. And that makes sense, right? Because maybe I just want to look at the one on the top. Right? Yeah, the degeneration is encoded on the boundary. It makes sense. That's how you should think about the special fiber is what happened on the boundary. Yes. Right, so now we can also do the same thing. So now when we restrict to the disk, we also want to measure the degeneration on the boundary of the subdisk, right? Yeah, of the corresponding subdisk over here. Yeah, maybe you different color. No, I don't want this guy. Yeah, so yeah, when you restrict to the subdisk, then you can also like measure the degeneration on the boundary of the subdisk. That help you to understand the degeneration of the subdisk. And somehow the degeneration will tell you whether your expanding is good or not. It's good expanding because there are many ways to expanding, right? Like there are many ways to deform things. So what way is good in our case? Yeah. Yeah. AKA, we want to understand the two following questions. The first one is how we measure the degeneration. Yeah, the degeneration is mean the data on the boundary that I talked about. How we measure it. And the second one is where to measure, because you know there are infinitely many subdisks inside here. Like what you only want to look at finally many of them, you know, and understand the whole things. Yeah, so how and where, that is what we want to answer. And for the first question, then the motivation again come from elliptic curve. Yeah, that's why when you do number theory, you want elliptic curve because it gives you a lot of motivation. The motivation is come from elliptic curve. Right. So when you have an elliptic curve over a local ring, a local field, for example, the ZP, right, periodic, for instance, then one thing is one nice thing about elliptic curve is you can always have the Weierstrass equation that is followed from the Riemann rock. Then you always have the Weierstrass. equation. Yeah, so it looked like this: y squared plus a1 xy plus 3 plus x cubic plus a2 x square a4x plus a6 and so on. So that is the Weierstrass equation. And then there are many equations, right? You can change a variable, then you have different model. However, there is something called a minimal model when the discriminant, right, is a polynomial over OK xy. It's a polynomial, so you can talk about the discriminant of the polynomial. And yeah, and the minimal model is when the valuation, right, the valuation here, the valuation of the discriminant, it one stand for the discriminant of the Weierstrass equation is minimal, right? And then the reduction of whether the elliptic curve has good or bad reduction is determined by the valuation of the discriminant. In particular, if the valuation here is equal to 0, then we say E has good reduction. And when it is greater than 0, then E has bad reduction. The elliptic curve has bad reduction. Oops. Okay, yeah, so it has bad reduction in this case. Right, so yeah, so that is the very nice invariant that helps us to understand the good or bad reduction for elliptic curve. And then actually it translates somehow something we can have something similar for covering of curves, cyclic covering. Yeah, so that is called the refined Swan conductor, which will play a similar role. Suppose phi is a cover of a disk, right? So this one is actually a closed disk, but it's not too important in this talk. Then, and we can define two invariants. The first one is the depth Swan conductor. Look like this. So depth Swan conductor actually is analogous, parallel to the valuation of the discriminant for elliptic curve. Yeah, for instance, it tells you when the depth Swan conductor is 0 if and only if the extension of the residue field is separable. If the extension of the residue field is separable. Yeah, so that's the first invariant, but there are more than that. The second invariant is called the differential Swan conductor. So it happens when the depth Swan is greater than 0. Then you define the differential Swan conductor to be some differential form over this one is the residue field. Some differential form. And what it tells you? Well, it tells you how the depth vary, or just the rate of change of the depth. We will talk about that soon enough, the rate of change of the depth. Right, so what I mean by that, because we are looking at a closed disk, right? So when you consider a closed disk, you can think the disk is contained in, some Riemann surface, right? The disk here is part of the Riemann surface, P1, AN, K, for instance. Then you can, one nice thing we have is the Berkovic projective line, right? So you have something look like this because the P1AN can be think of as a Berkovic projective line. So it is quite, but you have 0, maybe you have infinity over here, right? You have a point at infinity, and you have many other points. So it forms a Berkovic projective line. It's a little bit complicated, but the rate of change here, but you will have like many directions. So if you start, if you look at some subdisk, then you look at some vertex, some point on a Berkovic projective line. Then you can go different direction, right? You can go many direction. Can go many direction from one point. Then the differential Swan conductor somehow will tell you the rate of change of the depth on that direction of the Berkovic projective line. Now, so it's related to periodic geometry, if you're familiar with this. But maybe should go quick. Yeah, so a little bit about the variation of the Swan conductor thing that I talk about. All right, so now if I let ds contained in D to be a disk of valuation at least S, right? Because again, if we start with our disk D, right, then you can think D is D0 because it contains all the point with valuation greater than or equal to 0. Then ds is actually smaller, right? Because larger valuation mean closer to 0, right? Means smaller. Right. Then we can define a function from S to the depth this is the depth Swan conductor of the restriction of the function to the subdisk. Right. Yeah, so it means like on the disk you have the depth will tell you about the information on the boundary. Then if you go to S, then you have different information on the subdisk. Yeah, that is the function we define. The function from S to the depth of the restriction to the subdisk, ds from Q to Q. Right, so we have the function of depth, and it has some nice property. First, it is a continuous function. Yeah, so when you have continuous function in calculus, you know the derivative and you know how the function look like. And moreover, it is piecewise linear with integral slope. So it should look like this. And the second property actually tell you that the depth Swan conductor is enough to understand the rate of change at finally many points. Yeah, that's the second property of the function. And finally, the last one say it factor through a retraction that contain the branch locus. This is the branch locus of phi and the point at infinity. Right, so what it tell you, again, because we want to understand the depth, right, it tell you that, well, even that the Berkovic projective line is huge, maybe infinity here, maybe 0 here, but you only need to consider the point on the branch locus and infinity, right? So if the branch locus containing this point, then the tree like this, then the small tree like this, the all you need to consider, right? If these are the branch points, then all these the branch locus, the branch points. Then yeah, a smaller tree, a finite tree is all you need to consider, and it actually suffice to study the depth Swan conductor at the vertex of the tree. That's what it tells you. So you only need to measure at finally many places. So that answers the where, right? The how is the Swan conductor, and the where is the place, the vertex of the minimal Berkovic projective line. Right, and that is the Herbert tree. So it's quite technical, and I run out of time. Yeah, but that is, yeah, that's the tree we want to understand. And one of the key thing is the cover has good reduction if and only if the depth and the differential conductor follow certain rule that are asserted by the tree. It means if you look at the tree, immediately tell you that the cover has good reduction or not. Yeah. So maybe let me go to, that is one example of how, this is one example of how a tree look like, right? That is one example we talked before, because the cover here branch at 2 points, right? At 0 and at t to the 5th. So the tree gonna look like this. The minimal tree look like infinity, 0, and t to the 5th. And yeah, that is the Herbig tree, because we want to measure the differential at this place and this place. Right. So at this place you have this. This place would correspond to this. This place is correspond to this vertex. Right. And yeah, the vertex here will correspond to this place. Right, and it should be 0, right? Because we want it have good reduction, so it should be have 0 at the boundary, at the outside boundary. So because I don't have much time, I will talk about the sketch of the roof. Right. Again, our goal is given a tower of extension. So is our goal. And psi n minus 1 is the deformation of a subcovering. Then our goal is to construct something, some deformation for the whole tower, extend to the whole tower. Okay. So how we do that? Well, the first step, let's say, maybe step 1 is we, from the psi n, we can construct a Herbig tree. Yeah, the tree that look like a Berkovic projective line, minimal Tn minus 1. This the Herbig tree from there. Now, a Herbig tree look like this one. Right? Herbig tree look like this. Oh, sorry. Yeah, a Herbig tree look like this one. We can construct it from the psi n here. Then in step 2, I will extend the Herbig tree first. I will extend the Herbig tree to something that the good reduction, because the Herbig tree tell you about the good. Yeah, so step 2, I will extend the Herbig tree. Yeah, it's called a Z mod P to the N Herbig tree. So it's just a combinatorial object, but somehow it tells you how to partition the disk, like how to partition, how to look at the smaller disk, and how to and where to compute the Swan conductor. And finally, step 3 is the more technical one of this process, is to construct. Step 3 is, it's just the construction. Using periodic geometry, using I call non-Archimedean geometry, non-Archimedean analysis. Because the goal is to do analysis, right? So what we do is we simply expand, right? We just keep expanding, as I say at the beginning, right? We start with some Gn tilde, right? It's just some kind of like rational function, right? Some even I can assume it to be ai x to the I, where I is greater than or equal to 0. Some rational function. Then the Herbig tree will tell you about the restriction on these coefficient, right? Restriction some So the AI here is in R. Actually, the AI here is in R, right? So we can do analysis. We can talk about the norm, the valuation, and we want to control the AI using the information that give you from the Herbig tree. And you just do analysis, you modify a little bit. So it help you expand a little bit, and then you can do expansion. And the analysis actually tell you that the process will terminate, right? Because the limit exists. That's how the analysis come in. They exist like absolute max, absolute mean from the analysis, and the limit exists from because it is complete, right? Everything complete in some sense. Right. And that is and that's it. Okay. And I think that's the end of my talk. That's what I want to.
Okay, so thank you very much for your talk.
Hello?
Are there any questions?
Yes. Hello?
Yes.
Hi.
So what about any finite number covering?
What do you mean by? Can you say again? What is the question?
Not just P power.
Yeah. Right. Oh, you mean yeah? You want to talk about like infinite tower?
Is that an obstruction? Infinity power and any integer power, integer number covering.
Ah, okay. Yeah. So you want to talk about like if like what happened, like is there a way to like to do the same thing when you have like infinite towers, right? Like, is that what you ask? Is that the question? Do you want to? Yeah. So right. So for the infinite towers, then of course we can do the process for finally many steps. Yeah, that's a good question. Right. Yeah. Yeah, I know like how to do it. Like finally many. Like it means you can only look at finite index quotient. But for the if you consider the inverse limit, then I haven't thought well enough about that. I don't spend enough time.
So also now we are considering curve. What about higher dimension variety?
That's a good question. So actually the invariant, the refined Swan conductor can extend to more than 4 dimensions, higher than one coverings. But most of the results we know, most of the properties of the Swan conductor that we know is for curves. For curves. Yeah. So I think it's possible to extend for higher dimension, but you need more result about the refined Swan conductor. You need to know more about the refined Swan conductor in order to extend to higher dimension. Yeah, that's a good one. Because the refined Swan originally defined by Cato, if for dimension is for large dimension. Yeah, that's a good question. Does it answer your question?
Are there other questions?
Can I ask a question?
Yes.
So what happens if you consider other groups, like not cyclic group, but like any finite group and normal subgroup and quotient group? And so if a subcover deforms, then does it lift to like recover or bigger covering? Right?
Yeah,
do you expect there is a counterexample?
Yeah, so actually, yeah, so like not any covering in characteristic P lift to characteristic 0. That is one important point. Yeah, and about your question regarding other finite group, maybe not cyclic, then maybe if we consider, then I think it is possible, but you will need more information. Maybe right, for instance, maybe I should write down. So if the group, instead of cyclic group, maybe Z mod P to the N, a very simple one, semi-direct product of Z mod M, right, where M is branch P, right, for this case first. Then you need more. Then you can define a herbitry with extra information coming from the semi-direct product here. Need extra information on the herbitry. Then you can still say many things about the deformation. It will require like it will be more commutation. It requires more commutation for this one.
So you mean you put some extra assumption to have positive result, right?
Like I don't know whether one can always like
Uh-huh.
obtain the same result. But what I say is like we can also like define a herbitry. Like we can define a similar information. We can talk about similar data, like the refined one conductor and herbitries and so on. Like with extra information, like you put more information on the herbitry. And I think at least for the case like this, I conjecture, I don't know yet, but I conjecture that, well, yeah, we can obtain the same result for group like this, for a semi-direct product of a cyclic. And we can do something. Yeah, just conjecture. Yeah, I don't know for sure. Okay, does that answer?
Okay. Yeah, thank you.
Are there more questions?
I just have I need some point, but the ring R is intrinsic P, right? So we are working completely intrinsic P, or R is a bit ring here.
Oh yeah, right. Yeah, good point. Yeah, so everything here is in characteristic P. So spec R is in characteristic P. Yeah.
So you have a kind of rigid geometry in characteristic P, right?
Yes. Yeah. Yeah. You can also do okay, rigid geometry. Okay.
You know, if there is a corresponding how to say differential, I mean connection parallel to this theory of yours.
You mean in characteristic zero, right? You talk about you want a periodic one. Is that?
No, I mean characteristic P here. I said this theory does this have a kind of parallel theory for in the language of differential equation.
In the language of differential equation. Yeah, good point. I actually don't know. Yeah, I have thought about this one, but I don't know enough. Yeah, that's a good point.
Yeah,
because we talk about like periodic differential equation.
Yeah, but this one here is not. Yeah, so it's just another. There should be another theory somehow.
Yeah.
Sorry,
I don't know much about this.
Are there more questions? If there's no more question, then let's thanks Hui Dong again. Thank you very much.
Yeah, thank you.
And that's finished for today. And in 2 weeks, there will be another AGEA seminar, but next time will be in the morning. And please be noted that the time is a little bit unusual because we start 15 minutes earlier. That means that depending on where you are, the starting time will be 7:45, 8:45, or 9:45. So 15 minutes earlier than usual. So thank you very much for your participation. See you in 2 weeks.
Yeah, see you.
See you.